All right, so now I just want to reiterate really things we learned in a previous conversation and review the terms. Okay, so the equilibrium constant K is as follows. So first of all, we're going to appreciate that there's such thing called as the law of mass action. I'm not going to use this term a whole lot. I almost never use it, but it's important for you to hear it. The law of the mass action goes as this: when a reaction has achieved equilibrium at a given temperature, the reaction quotient always has the same value. The reaction quotient has the same value when a reaction is at equilibrium, okay? So the value of Q then, when the reaction is at equilibrium, is called K. We said this in a previous conversation. So we know that QC this is QC at any point in the reaction, but at equilibrium, it's K, right? So QC and K are the same at equilibrium. Now, it's important, I think I want to point out, remember in a previous conversation, let me go to a different color. Remember this, the rate law? Rate is equal to K times A times B, maybe X and Y. Remember this is the rate law. This K is a lowercase k, and this is an uppercase K. These are not the same thing, so do not confuse the equilibrium constant with the kinetic rate constant K. All right, so suppose again we have some reaction. A plus B produces C plus D, where it's A moles of A plus B moles of B, right? QC at any point is given this form. And when the reaction is at equilibrium, it's also equal to Kc, which has the same form, okay? Same form, exactly. The equilibrium constant K is the same form as the reaction quotient Q, except K means it's at equilibrium and Q, it's at any point. All right, let me go back to red here. I'm not liking that blue. The value of the equilibrium constant is independent of the starting amount. The ratio that you have of the reactants and products is constant if it's at equilibrium, okay? And it doesn't matter what you started out with. The ratio is constant. However, the value does depend on the temperature of the system, right? So oftentimes we're going to simply say at 25 degrees Celsius, we're going to throw that in there, and it's going to seem like a throwaway phrase, but it turns out the equilibrium constant does depend on the temperature, and so we'll tell you what the temperature is, or the question writer will tell you what the temperature is, and it's going to just sort of be in the background. But do know that if the temperature changes, K does change, all right? So the magnitude of an equilibrium constant indicates the extent of a reaction. It tells you how far a reaction is gone, or how many products there are for every reactant, right? And K and Q are unitless values, and we'll say anything about that right now. We don't have units for those. Now, if K is very small, right, remember that K looks like this. K, this is a capital K, right? The concentration of products over the concentration of reactants, right? If K is very small, that means this is small. It means the product is small compared to the reactants, right? So if K, let's say, I'm going to make up a number, all right? So suppose that K for a particular reaction is equal to 0.001. And that would mean that you have one product for every 1,000 reactants, right, in terms of moles, right? So that means that the reaction mixture contains mostly reactants. That means the denominator is much bigger than the numerator. However, if K is very large, let's say K in a different reaction is 1,000, or let's say 10,000, make it even bigger, okay? This is the same thing as, watch this, 10,000 to 1. And that means that at equilibrium, mostly we have products, okay? The value of K, though, this is an assumption which is tempting to make, the value of K gives no indication as to the rate. It says nothing about if the reaction is fast or slow. It only tells you what the ratio of the products to reactants is at equilibrium.